Okay, so for this last example, we are going to figure out the empirical formula of a compound from its percent by mass composition analysis. This is problem 3.83 on page 130 for your reference. Okay, so reading the problem, we say, what is the empirical formula of a compound that is 48.64% carbon, 8.16% hydrogen, and the rest is oxygen? Okay, so the rest is oxygen. Maybe this was figured out by combustion analysis, so they couldn't directly analyze the oxygen. But in any case, it's a simple matter to calculate 100 minus 48.64 minus 8.16 is going to equal 43.2% oxygen. And so now we can simply set up a table where we have carbon, hydrogen, and oxygen, and we can use the percent by mass analysis to figure out how many moles of each we have. We want to convert mass ratios, mass percentages into mole ratios. And so we're going to just assume we were given 100 grams of this stuff because that makes converting the percents into actual masses very easy. That would mean we would have 48.64 grams of carbon. And of course, if we want to know how many moles that is, we would divide that by 12. We would multiply it by 1 mole divided by 12.011 grams of carbon, right? And doing it this way ensures that we get the units right and dimensional analysis works out. And so this equals 4.05 moles of carbon. Notice that I'm not just rounding it off to 2 places. I'm actually keeping 3 places of significance. That's usually a good rule of thumb on how many digits you need in order to get one of these questions correct. All right, so now let's go on to the hydrogen. We have 8.16 grams of hydrogen times 1 mole divided by 1.008 grams. All right, so that's the reciprocal of the atomic mass of hydrogen, again, looked up off the periodic table. And so that's going to equal 8.10 moles of hydrogen. And for the last one, we're going to take our 43.2 grams of oxygen, multiply that by 1 mole of oxygen over 15.999 grams. And that's going to equal 2.70 moles of oxygen. Okay? So now that we have the moles of each of those, we can set it up in terms of mole ratios. Right? So the mole ratio, carbon to hydrogen to oxygen, is 4.05 to 8.10 to 2.70. And looking at that right off the bat, right, we've got decimals, and so we're going to want to convert these into whole numbers. And a good way to start that process is by dividing out the smallest one and seeing if things get any simpler for us, right? So if we do this, we divide all of them by 2.7. Okay, and now that means that we're going to get 1.5 to 3 to 1. 1.5 to 3 to 1. Okay, and it should be pretty easy to see what you need to do to convert those into actual whole numbers, right? You just need to multiply by 2. So this becomes a 3, this becomes a 6, this becomes a 2. And now we have our final answer. We can directly read this off as an empirical formula, C3H6O2. So this is a pretty typical example of how to take a percent mass composition like this one. First, you convert it into moles by assuming you have a 100-gram sample and converting and using the atomic masses of each of the atoms in the formula to get the moles of each atom type. And then you simply divide out whichever one of those is the smallest number. If you divide that out of each of them, you're going to get close to a whole number ratio. It may take you a couple of steps like we did here. We noticed that one of our numbers was 1.5, so the way to make that into a whole number is to multiply by 2. If it had been 1.33, then we say, oh, well, now we need to multiply that by 3 in order to make it a whole number, okay? And so on and so forth. You kind of get used to those when they're small integers like a fourth, a third, a half. You should kind of have those at your fingertips so you can pretty easily go from a distribution like that to a distribution like that and get your empirical formula.